Today we are going to be looking at applications of slope fields and differentials and how the AP applies them. So the first question we're going to take a look at comes from the 2006 AP exam. And it asks us to, of course, consider the differential equation. So this is a differential equation right here where x cannot be 0. Remember, they're not going to say it's not x cannot be 0 because it's going to be undefined at that point right here. So remember, this is a derivative, and that's going to give us what the slopes of the function looks like. And matter of fact, that's part A right here. And it says on the axis provided, sketch the slope field with a given differential equation at the 8 points indicated. So my first point they have me here is at -2, 0. So at -2, 0, I can find the slope by plugging it in. My y value is 0, so we would get 1 plus 0 over -2. So it's a slope of -1/2. So we go over here, do the best we can, try to make a slope of -1/2. It doesn't have to be perfect. And then I'm going to go through and do the next bunch right here. So my next one would be at the point -1, +1. The slope here, well, this becomes 1 plus 1, which is 2, over x, which is -1. -1, and of course that becomes -2. And so over here at -1, 1, we have a slope of -2. It's pretty steep, so draw it kind of steep. And I just keep going. -1, 0. Oops, I should have -1, 0. Yep. To get this slope, this is saying y plus 0, so that's just going to become 1 over -1. So that's a slope of -1. So slightly less steep than the first, this one up here. My next one, -1, -1. And our slope here, this says y minus 1, which is 0, so it doesn't matter what the bottom is, that's just a 0 slope down here. And they don't want me to put anything on the x-axis because they said x cannot be 0, so don't put anything there. And I go over to the other side. My extreme one, I'll go over here at 2, 0. The slope here would be 1 plus 0 over 2, so 1/2, +1/2. 1, 1. What's that? 1 plus 1 over 1, so it'll be 2 over 1, which is just 2. +2, so make sure it looks like a +2. There it goes. And we have 1, 0. So that's going to become 1 plus 0 over 1, so 1 over 1, which is 1, so a slope of 1. They don't have to be perfect, but you got to give an idea that you know what they look like. And down here, 1, -1. Our slope would be, of course, 1 minus the -1. Remember, this was a 1 there. Whoops, that was a 1 there. And that becomes 0. So our slope here is 0. And for me, it looks like an angry eyes or something like that. And that would be our slope field. Now, you don't have to list out the points. You can do that work in your head. I like to list it out just to make sure I'm getting the right values there. All right. For part B, it says find the particular solution for y equals f of x to the differential equation given our initial condition. So what are they saying to solve for the particular solution? They want us to solve for y. So this is going to be our antiderivatives right here. So when I write it out, we're going to get this dy dx. That's what we've been working on. 1 plus y over x. And if I separate out, this becomes, separate my variables, 1 over 1 plus y dy equals 1 over x dx. Oh, this looks kind of funky. We never dealt with one with 2 natural logs. I wonder what's going to happen. The first one, not that bad. That's just a natural log of the absolute value of x plus c1. Now for this one, though, I am going to use my u substitution. So I know u is going to be 1 plus y. My du is just dy. This is what I want. There's nothing I'm going to multiply or divide by there. So this just becomes then the natural log of 1 plus y. And now let's see. This is going to be kind of cool. We're going to exponentiate both sides. E it. And we're going to get the absolute value of 1 plus y equals e to the natural log of the absolute value of x times e to the c1. Be careful. I'm not going to get rid of this just yet. I'm going to go take care of my constant right here. We're going to let e to the c1 equal c2. And that's going to give me the absolute value of y, absolute value of 1 plus y equals c2 e to the natural log of the absolute value of x. Now I'm going to go and take care of this. This is like an extra little step for us right here. E and natural log cancel each other out. So we're left with the absolute value of 1 plus y equals c2 times the absolute value of x. Don't cancel out that absolute value of x. It's very important for us. So what we're left with is 1 plus y equals c2 times the absolute value of x. Remember, it's really a plus or minus c2. It's really a plus or minus c2, but it gets absorbed, so we don't worry about writing that out. You don't have to do that. All right, so here's our equation. Now notice, we will get two answer choices. We get two answers. That's what that absolute value is kind of telling us. We're going to get two possible solutions right here. So let's see, when we solve this, we're going to use our initial condition, which was 1. So when I solve this one, we're going to have to find c2, we're going to use our point negative 1, 1, and we plug it in, we're going to get, what's that, 1 plus 1 equals c2 times the absolute value of negative 1, which is just 1. So what is c2 going to equal? But 2. So our equation is going to be y equals 2 times the absolute value of x minus 1. And there is our equation. Now, there is one more point on this one for the AP. There is a domain restriction right here. Remember we said there are two answers because of the absolute value. Which one do we want? Well, if we draw the absolute value of x, we know what that looks like. Right here. Well, I'm at the point, so I got this line, this part, and I have this part. And, well, we're at the point negative 1 up 1. Well, what is that telling us? Our x values are negative. So our restriction says that x has to be between negative infinity and 0 for this to work. And there is our complete answer right there. Now, another way to think about the domain here is f of x needs to be continuous and differentiable. Remember, we are not differentiable at 0. So, now you might be asking, why did I put a hard bracket at 0? Well, you could put a soft bracket there, but there are some books that talk about local differentiability. At 0, it could be considered differentiable on a single side. So you can put either one. I think AP will be okay with either one in this case. And why do we pick the negative? Because our initial condition was x was negative. Remember, we always used to say, well, y would it be plus or minus? But here we're saying x is plus or minus. So this is a tough question right there. That was worth 1 point on the AP. Only many people got that part. All right, the last part for part C for this example, it says let f be a function that satisfies a given differential equation. Write the equation of a tangent line, there it is, a tangent line to the curve at the point negative 1, 1, and use it to approximate the value. So this is just our tangent line approximation. We've done lots of these. It's been a while, so let's review this. Well, with a tangent line, there are two things we need. We need a point, which they've given us, and we need the slope. To get the slope, we're going to use the derivative, which they told us was this 1 plus y over x. Now, at the point negative 1, 1, we know what the slope is. We already got it above here. At negative 1, 1, the slope was negative 2. If you forgot, you can just plug it in, 1 plus 1 over negative 2, over negative 1, excuse me, and that becomes negative 2. So our tangent line, y minus 1 equals negative 2, x plus 1. There's our tangent line. And so to approximate at negative 0.9, we can just plug that in. Y minus 1 equals negative 2, negative 0.9 plus 1. And we get y minus 1 equals, what does that become here? Negative 0.2. And if we add, y is about 0.8. And there would be our answer right there. So even there, we see a tangent line approximation. Now, what if I wanted to find the actual value at 0.8? We would plug in here. And I can do that. To get the actual value, I would plug it into our equation. And I think in this case, we might actually get the same answer. Mainly, and that's only really because, well, let's see what we get here. We get y equals 2 times the absolute value, 0.8 minus 1. What does that become? 1.6 minus 1. So y is actually negative 0.4 in this case right there. I guess so. Anyway, so to get the actual value, negative 0.9, I plugged it in wrong. Negative 0.9, there we go. That's 1.8 minus 1, and that is 0.8. I messed up on my subtraction anyways. So we actually get the same answer, but that's really because that's the absolute value. It's a line already for us, so we should expect to get the same answer there. Forgive my error. Mr. Warnout sometimes cannot do the math right. Anyways, I hope you did enjoy this video, and I will see you later. Bye-bye.